All right. Welcome back, everybody, to another exciting session of CE 397, Controlled Theory for Smart Infrastructure. So last time, what did we talk about last time? In the last class, we talked about finding particular solutions to LTI systems, and I gave you one method for doing so. What I would characterize as, the most general method for solving LTI dynamical systems, and that is via convolution. So we showed that if you take a input to a system and you convolve it with the system's impulse response function, then you can produce the particular solution corresponding to any arbitrary input to the system. So again, we're taking, we have some system, we have some input U of t that's a function of time. We have the impulse response of the system, which characterizes the response of the system to an impulsive input, which we defined. And we showed that when you convolve those two together, you can get the particular solution or the response of the system to any arbitrary input, okay? And convolution we defined via the following convolution integral. Okay, so just to kind of conceptually recap what we're talking about when we're talking about convolution impulse response. So the central idea here is that for any system, for any dynamical system, if you take that system and you hit it with an impulsive input, so an input that is instantaneous, it'll produce some response, which we'll call the impulse response. And this will generally be in the form of some complex exponential. So a combination of exponential growth or decay and some set of sinusoidal response. Okay, so every system we have, we can take it, we can hit it with an impulsive input, and that response is unique and is called the impulse response of the system. Thus, we can think of any arbitrary input to the system as being represented by a train of impulses. So any input signal to the system you can think of as just a bunch of little impulses added together in sequence. And each one of those impulses produces some scaled impulse response. Thus, we can obtain the solution or the response of the system to any arbitrary input by going through essentially hitting the system with all of those little impulses, computing the responses to each one of those impulses, and then adding them up via integration. Okay, so this is conceptually what's happening when we are performing convolution to determine the particular solution. We are summing up the responses to all of those little impulsive inputs, with each one being scaled by the envelope of the function here. Are there any questions conceptually on impulse response and convolution before we move on? And as I mentioned before, often in dynamical systems or in civil infrastructure systems, we're interested in obtaining the impulse response for a system or approximating the impulse response for a system. So this is often used in the domain of what's called system identification, where you take a structural system, for instance, you hit it with an impulsive input. So you take it and you literally hit it with a hammer sometimes in the lab. And from that, you can characterize the system's impulse response and thus determine its response to any arbitrary input like an earthquake, for instance. Okay, so it's important practically as well as theoretically. Unfortunately, convolution is not always easy to do. So we went through a couple examples in class. I showed you how you could use convolution to compute the particular solution to an RC circuit, and that one wasn't too bad. But in the general case, it's not always going to be easy. So last time in class, we finished off by looking at the response of a structural system, and we went through and we derived the homogeneous response of that structure. I'll just very quickly go through and show what it looks like when you try to compute the particular solution of that structural system using convolution. And you will see why it may not be the approach you would like to use. Okay, so first, let's look at what the impulse response of the system is. And for the RC circuit, I showed you that the impulse response could be thought of as essentially being equivalent to the response of the system to some initial condition. For a structural system, it's very much the same. And I won't go through this derivation just because we don't have time. It's very similar to the explanation I showed you for the RC circuit. But for a structural system, the impulse response is equivalent to essentially imparting a unit input of momentum to the system, which corresponds to starting with a non-zero velocity. Okay, so for the RC circuit, we showed that it was equivalent to starting with some non-zero voltage across the capacitor. For the structural system, it's equivalent to starting with some non-zero velocity. In particular, velocity of the structure at time zero equal to 1/m. Okay, and I can post some supplementary material for how this happens, but you can essentially think of the response, the impulse response, as being equivalent to starting with some non-zero velocity. Okay, so if we go back here, we showed last time that for the RC circuit, we could determine the impulse response essentially by simulating the homogeneous response to that initial condition. So what would the impulse response of the structural system be if it's equivalent to starting with a non-zero velocity and a initial displacement of 0? What would the impulse response be? Looking at our homogeneous solution here. So it's equivalent to the homogeneous solution where x dot at time 0 is equal to 1/m and x0 is equal to 0. So if we went and we plugged those in to this homogeneous response, what we would end up with is e to the negative zeta times the natural frequency times time times, so if we go in and plug in x0 equal to 0, x dot is equal to 1/m, what we would get is an impulse response of 1/m omega d times sine of omega dt. So sorry? Yeah. So the impulse response, as I mentioned, this is kind of a hand-wavy explanation. And today, when we get to Laplace transforms, I'll give you a specific formula for computing the impulse response. But in this case, it's equivalent to starting with a velocity of 1/m. Okay, and so if we plug that into the homogeneous response, we get the following impulse response function. Okay, so how do we compute the particular solution to this structural system? Let's just say we have some arbitrary input ut. So the response of the structural system will be yp of t is equal to the integral from 0 to t of u tau times 1/m omega d e to the negative zeta times the natural frequency times time times sine of omega d t minus tau d tau, where this is our input and this is our impulse response. And that looks kind of yucky, right? Computing this convolution integral for a non-trivial input ut is not easy to do, which is why in this class, what we're going to do is we're going to show you a much simpler method for computing the particular response of systems that is equivalent to doing this. What we're going to do is we're going to take the system and we're going to transform it from one basis to another. In particular, we're going to go from the time domain, which we've been working in so far, to the frequency domain using Laplace transforms, which you may be familiar with. Did you have a question, Jimmy?
Yeah, is the exponential have t minus tau?
Right, sorry, that should be t minus tau. Very good. Okay, so I will just write, this is Yaki. Fortunately, there is a better way. Great. So what I want to do now is I want to give you a kind of a high-level overview of what the Laplace transform is and why we will be using it. Today, we will be going into the frequency domain. And going into the frequency domain today. Great. So let me just give you a high-level overview of what a Laplace transform is. So who here is familiar with Laplace transforms? This is probably something you visited in undergraduate differential equations. Who remembers what a Laplace transform is? Who's used one recently? Has anyone used them in graduate school? A little bit. So are there any volunteers who want to kind of volunteer what their intuitive explanation for what a Laplace transform is? So is there any kind of concepts we can think about? So what does it mean when I say we're going to go from the time domain to the frequency domain? Does that kind of jog your memory a little bit? Right. So I think often Laplace transforms are introduced in undergraduate differential equations. You show the procedures for how they're used, but it's not really explained what it's doing. The key idea is that a Laplace transform is a change of basis. So it's a change of basis that maps our functions from one domain to another. And for this class, Laplace transforms will make that change of basis will make it easier to find the particular solutions by transforming convolution problems into simple multiplication problems. Okay, so it's a change of basis from the time domain to the frequency domain. And who knows what I mean by frequency domain? What do I mean by frequency domain? Sorry? It's the inverse of the time domain? You could think of it as an inverse of a time domain, and that we will need to apply an inverse Laplace transform to get back to the time domain. But so who's familiar with Fourier transforms? Okay, most of you are familiar with Fourier transforms. So what are Fourier transforms doing fundamentally when you take a function from the time domain and apply the Fourier transform? So you break it into an infinite series of sines and cosines. Very good. What is a Laplace transform doing? Right. So the Fourier transform takes a function in the time domain and breaks it into an infinite. Oh, sorry, I should make a caveat here. What types of functions can Fourier transforms be applied to? There's a constraint here. Continuous, but also something else. Sorry? It doesn't necessarily need to be sinusoidal. Fourier transforms can only be applied to functions that are periodic. Fourier transforms will only work on functions that are periodic. Think about, if you have a function that's growing over time, how could you represent that with this infinite series of sines and cosines? You can't, because they all have a constant magnitude on average. So much like a Fourier transform converts a function into an infinite series of sines and cosines, the Laplace transform is a generalization of the Fourier transform that represents a function in a new basis, where that basis consists of complex exponentials, right? So, which includes your exponential growth and decay terms, as well as the sinusoidal terms from the complex exponential. Okay, so let's say we have a function. We have the time domain. We have the frequency domain. And let's say we have a function in the time domain. Okay, what we're going to do is when we put it into the frequency domain, we're going to have that same function, but we can represent that function as an infinite sum, so an integral of complex exponentials. So, i.e., sinusoids that grow or decay over time. So this can be applied to any continuous function, right? We're taking this function and we're decomposing it into a new basis, a basis of complex exponentials. That kind of asks the question, what basis were we in before? So if the frequency domain is the basis of complex exponentials, what is the time domain composed of? Anyone want to guess? Sorry? So if the frequency domain, we can represent any function in the basis of complex exponentials. So we can get any function by adding together complex exponentials. What basis were we in the time domain? It's kind of a brain teaser. In the time domain, we were in the basis of Dirac deltas. Remember that I showed you that any function in the time domain can be written by a train of Dirac deltas or an infinite sum of Dirac deltas. So what we're doing when we're taking the Laplace transform is we're taking that function in the basis of Dirac deltas and we're rewriting it in the basis of complex exponentials. So it's analogous to a Fourier transform, right? So here our basis is the Dirac deltas. Here our basis is the complex exponentials, where we'll just say sigma is in the complex numbers. Okay. So hopefully that kind of gives a higher level overview of what Laplace transforms are. Are there any questions about kind of this conceptual overview of what the Laplace transform is? Any questions? Okay, so with that, let's go ahead and define the Laplace transform. There's actually two types of Laplace transforms. There's the bilateral transform and the unilateral transform. In this class, we'll just be dealing with the unilateral transform because we're primarily going to be dealing with systems that start at time 0. But there is also a bilateral transform that you can also define. But in essence, the Laplace transform is defined as follows. Okay, so when we're taking the Laplace transform of a function f of t, so let me just write this. When we take the Laplace transform of a function f of t, this gives us a function that I will call big F of s. So when I write big F, that means that we are in the frequency domain now. And instead of our variable t for time, we have a variable s that represents our frequency. Okay, so the Laplace transform is defined as follows. Okay, so we have that big F of s is equal to the integral from, for the unilateral transform, it'll be from 0 to infinity of ft e to the negative st dt. Okay, so you're taking your function f of t, you are multiplying it by e to the negative st, and you are integrating it over t from 0 to infinity. So the t integrates out, and you end up with a function f of s. And this is taking us from the time domain t to the frequency domain s. Similarly, we will also be using an inverse Laplace transform. And what do you think this does? What do you think the inverse Laplace transform does? Right, so we took it from the time domain to the frequency domain. We also have a method for taking us from the frequency domain back to the time domain. In general, this is more difficult to compute. So we'll show you some tricks for doing this, but the inverse Laplace transform is defined as 1 over 2 pi j, where j is the imaginary unit, integrated, I'll draw the limits in a second, integral of big F of s, e to the st, no negative, ds, where the limits of integration go from sigma minus j infinity to sigma plus j infinity. So it's integrating over the imaginary axis. We're never going to actually use the inverse Laplace transform formula in this class, but I want to make sure that you have that definition here. Mostly when we are going to be doing Laplace transforms and inverse Laplace transforms, we will be using essentially tabulated forms of these equations. So you look up the transform in the table. Okay, so let's talk about why we use Laplace transforms in this class. Why use Laplace transforms? The answer is that for the purposes of this class, the Laplace transform allows us to, instead of computing that complicated convolution integral, it allows us to compute the particular solutions to LTI systems by multiplying the input to the system and the impulse response in the frequency domain. Okay, so whereas before in the time domain, we had to convolve the impulse response with the input to the system, if we take it to the Laplace domain, if we take it to the frequency domain, we can compute the particular solution or that response by just simply multiplying the input and the impulse response in the frequency domain. And in the frequency domain, the impulse response has another special name, which I'll talk about, called the transfer function of the system. Okay, so why use Laplace transforms? It allows us to solve convolution integrals as simple multiplication problems. Okay, so I will show you now a really interesting fact, which is I will prove to you that convolution in the time domain is equivalent to multiplication in the frequency domain. Who's familiar with this concept, by the way? Has anyone seen this before? Okay, it's pretty fascinating. Okay, so let's say that we have some function in the time domain, y of t is equal to the convolution integral from negative infinity to positive infinity of u tau h t minus tau. So this is, for instance, the particular solution corresponding to some system with an impulse response function h and an input u. Okay, so let's take this and let's go ahead and apply the Laplace transform. So we're going to take the Laplace transform. Let me just draw it up here. We're going to take the Laplace transform of this entire thing. And what we end up with is this becomes y of s is equal to the Laplace transform of this integral from negative infinity to positive infinity u tau h t minus tau d tau. Okay, and let's just apply the definition of the Laplace transform. Remember that it's the integral of our function f with e to the negative st dt. So let's go ahead and apply that definition. We'll end up with a double integral from 0 to infinity. And let's just say that our input is only defined from u to t. So this integral here, instead of from negative infinity to positive infinity, let's just say it's from 0 to t. Okay, what we have is u tau h t minus tau d tau times e to the negative st dt. So we have this double integral here. Okay, and let's make this problem easier by switching the order of integration. Okay, so we have an integral in terms of d tau dt. We're going to switch the order of the integral. So just to recap on switching the order of integration, let's say we have, some function of two variables. It's kind of like a review of, review of some calculus concepts here. Let's say we have a function of two variables. I have to just decide how big to make it here. I'm going to draw it twice here. Okay, so here we have that the x-axis is tau, the y-axis is t. We have a function of two variables in terms of t and tau. Okay, so maybe it looks like some contours coming out of the page here. And we want to integrate this function over both t and tau. So there's two ways we can do this. This line here is t equal to tau. There's two ways we can do this. The first is we first integrate over tau and then integrate over t. So the first way is we integrate our function f from tau equals 0 to t. So we integrate this way. So we integrate the function over tau equals 0 to t. And then we just add up all those ribbons in the vertical direction. Okay, so that's one way we can integrate over two dimensions. The other way we could integrate is integrate first in the vertical direction from t equals tau to infinity. And then add up these little ribbons in the horizontal direction. Okay, so what we're going to do is we're going to switch the order of integration from one to the other. It'll make it a little bit easier to solve this problem. So let me just write this out. In this way, we integrate from tau 0 to t, and then add up ribbons vertically. Second way is we integrate from t equals tau to infinity, and then, add up ribbons horizontally. Okay, so let's apply that logic here. We're going to switch the order of integration from d tau and then dt to dt and then d tau. Okay, so switching the order of integration, instead of tau from 0 to t, we now go from t tau to infinity and then tau from 0 to infinity. Okay, so we have that y of s is equal to the double integral 0 to infinity, tau to infinity of u tau h t minus tau e to the negative st dt d tau. So we switched the order of integration. We had to change the limits of the integral accordingly. Okay. And okay, so looks like we're kind of getting somewhere. Next, I'm going to take this function, I'm going to multiply it by 1. I take this integral and I'm going to multiply it by 1. Okay, so we have the double integral from 0 to infinity, t over tau to infinity. I'm going to multiply by 1. I'll express 1 as e to the negative st, e to the st. Okay, so this is just equivalent to taking our function, multiplying it by 1. And the rest will be the same, u tau h t minus tau e to the negative st dt d tau. Okay, and now we can separate this out. So we have our first integral from 0 to infinity. Let's take the terms that don't depend on t and pull them out. So we have u tau e to the negative s tau times the integral from tau to infinity of h t minus tau e to the negative s t minus tau. That looks promising. dt d tau. Okay, so that looks promising. Okay, so now what we're going to do is we're going to take, instead of t, we're going to define a dummy variable. T prime is equal to t minus tau. Okay, so t prime is equal to t minus tau. We have that dt prime by dt is equal to 1 minus 0. And so dt prime is equal to dt. Okay, so what we can do is we can take this integral here and we can integrate it, instead of over dt, we can integrate it over dt prime, which is equal to t minus tau. Let's go ahead and substitute. And what we get is ys is equal to integral from 0 to infinity of u tau e to the negative s tau d tau times the integral 0 to infinity h t prime, h t prime e to the negative st prime dt prime, where t prime is equal to t minus tau. Okay, so what is this here? What is this integral here? So we have some function u tau, we're multiplying it by e to the negative s tau, and we're integrating it from 0 to infinity. What is that? It's the Laplace transform of u. So this is u of s. What is this here? Sorry? Right. So the t prime is just kind of the variable itself. Doesn't necessarily mean anything. We're just integrating over it. So this is the Laplace transform of, right, which is also Laplace transform of h of t. So what we get is h of s. So we have that y of s, our particular solution in the frequency domain, is equal to u of s times h of s. Okay, where u of s, this is our inputs in the frequency domain. And h of s, this is our impulse response in the frequency domain. Right. And this has a special name. The impulse response in the frequency domain is also called the transfer function. I'll be using this term a lot. So in summary, convolution in the time domain is equivalent to multiplication in the frequency domain. Which means that if we want to compute the particular solution, if we want to compute the response of the system to some arbitrary input, all we need to do is find the impulse response, convert that to the frequency domain, convert the input to the frequency domain, and then multiply them together. Okay. And then we have to take that solution and put it back in the time domain. But altogether, that is usually much easier than performing that complicated convolution integral. Okay. All right. Very good. Are there any questions? Any questions on this concept before I move on? Well, has anyone seen this equivalence before? No? Okay. Note that the same thing applies to the Fourier transform as well. Right, convolution in the time domain is also equivalent to convolution in the frequency domain when you use the Fourier transform as well, just for when you're dealing with periodic functions. So let's just quickly recap the solution strategy. Okay, so we have some dynamical system. Let's say we have, in this case, I'm going to write our system in terms of h of t. Okay, it represents the impulse response of the system. We have some input u of t, produces some output y of t. So we can compute the response of the system more easily by taking each of these terms, so the input and the impulse response, converting them to the frequency domain, and instead of solving that complex convolution integral, we can solve for the particular solution using simple multiplication. Okay, so just pictorially, we start with some input u of t. Okay, our y of t is equal to the convolution integral of u tau h t minus tau d tau. And that will give us our particular solution yt. This is from 0 to t here. Okay, so instead of performing this complicated convolution integral, what we can do is first convert our input to the frequency domain by applying a Laplace transform to the input. We take the impulse response, we apply the Laplace transform to compute the transfer function h of s. And then we can obtain the solution y of s by simply multiplying u of s by h of s. And that gives us the solution in the frequency domain. Then what do you think we need to do? Take the inverse Laplace transform to get the solution in the time domain. That is the summary of our solution procedure. Who's seen this? Who's used this procedure before in differential equations? Cool. Anybody else? Yeah? Yeah, okay. So that's the general solution procedure. Just give me a second here. Okay. So the next thing I want to do before I move on to actually applying this is I want to give you some properties of Laplace transforms that are going to be needed later. So Laplace transforms are a really fascinating topic. I'm going to give you my top 8 properties of Laplace transforms. My top 8 properties. Who remembers top 8s from MySpace? Nobody? Is anyone that old that they remember MySpace? Okay, so now I know I'm officially past the age where I can make that reference. But this is nevertheless my top 8 properties of Laplace transforms. So quickly, let's just kind of make a note on our notation here. Let's say we have a function f of t in the time domain. We apply a Laplace transform and we get a function f of s in the frequency domain. So that's the notation I'm going to be using. Okay, I love drawing that little L symbol. It's my favorite mathematical symbol to draw, I think. So I'm just going to keep doing it. All right, property number 1, linearity. So the Laplace transform is a linear operator. You can verify this mathematically, but let's say we have F1 maps to big F1. So F1 of t maps to big F1 of s. F of 2 of t maps to big F2 of s in the frequency domain. If we apply the Laplace transform to alpha F1 of t plus beta F2 of t, this will become alpha F1 of s plus beta big F2 of s. Okay, so the Laplace transform is a linear operator. This is going to be very important later on. Okay. Property number 2, time delay. Okay, so if we have a function f of t that maps to f of s in the frequency domain, if we take our original function in the time domain and we delay it by some time tau, so now when I'm writing f of t minus tau, that means we're shifting the function by tau to the right. If we take that shifted function and we apply the Laplace transform, it's equivalent to taking our function f of s in the frequency domain and multiplying it by a complex exponential e to the negative s tau. Okay, so shifting our function in the time domain is equivalent to multiplication by a complex exponential in the frequency domain. All right. Property number 3, time scaling. Okay, so as before, we have a function f of t that maps to big F of s in the frequency domain. If we take our function and we scale the time by some constant alpha, what we get in the frequency domain is kind of the inverse. We get 1 over the absolute value of alpha times big F of s divided by alpha. Okay, so scaling the time by some constant in the time domain kind of leads to the inverse behavior in the frequency domain. It's equivalent to dividing by that same constant scaling. All right. Property number 4, frequency shift. All right, so we have a function f of t in the time domain maps to big F of s in the frequency domain. If we take our function in the time domain and multiply it by a complex exponential, that will become equivalent to taking our function in the frequency domain and adding that constant to our frequency. Okay, so it's equivalent to shifting our frequency. So, you know, what property is this similar to? Right. So it's the opposite behavior for what we saw with the time shift, right? So shifting the frequency is equivalent to multiplying by an exponential in the time domain. Okay. All right. This next property is probably the most important one for this class, and that is differentiation. You will be using this a lot. So let's say we have a function f of t in the time domain that maps to big F of s in the frequency domain. If we take that function in the time domain and we differentiate it by t, we get s times big F of s minus our initial condition in the time domain. So note here this f of 0, this is not f of 0 in the frequency domain, this is our initial condition in the time domain. Okay. Similarly, if we take the second derivative of our function f with respect to time and apply the Laplace transform, it maps to s squared times f big F of s minus s times our initial condition f0 minus f dot of 0. Okay, so this is our an initial condition, and this is the derivative of our initial condition. So when you get to higher order systems, you'll end up with higher order initial conditions as well. Okay, and this applies so on and so on for derivatives of higher order. So this is the property that you'll be using most in this class. If you take the derivative of your function in the time domain, it's equivalent to multiplying by s in the frequency domain. Okay. All right. Are there any questions before I move on? Okay. Property number 6, convolution. So this is the property that I showed you towards the beginning of class. If we have a function f1 of t that maps to f1 of s, f2 of t that maps to f2 of s. Okay, if we convolve f1 of t with f2 of t and take the Laplace transform, what is that equivalent to? Oh, sorry? So this is the property that we showed earlier. So convolution in the time domain is equivalent to what in the frequency domain? Multiplication, exactly. So we have big F1 of s times big F2 of s. This is the property that makes it really easy to use for solving particular solutions. All right. Next property is pretty fascinating. Multiplication. Okay, so let's say we have a function f1 of t that maps to big F1 of s in the frequency domain, f2 of t that maps to big F2 of s in the frequency domain, and we take f1 of t and multiply it by f2 of t, and we apply the Laplace transform. What do you think this becomes in the frequency domain? Not sure. If you were to guess based on the other properties I've showed you, what do you think multiplication in the time domain corresponds to in the frequency domain? Convolution. Right? If you take f1 and f2, you multiply them in the time domain, that's equivalent to big F1 of s convolved with big F2 of s. So convolution in the time domain is equivalent to multiplication in the frequency domain. Multiplication in the time domain is equivalent to convolution in the frequency domain. So pretty fascinating. All right, and the final property, you're probably not going to ever use this one in this class, but this is multiplication by time. And it is kind of the opposite of one of the other properties that we showed earlier. Okay, if we have a function f of t that maps to big F of s, if we take that function f of t and multiply it by time, in the frequency domain, this maps to negative d by ds big F of s. Okay, so what rule is this kind of the opposite of? Differentiation, right? So, with most of these rules, you get kind of the opposite behavior going from one domain to the other. So it's really fascinating, really a fascinating mathematical function, Laplace transforms. All right, so are there any questions on Laplace transforms and their properties before I move on? I'm running a bit slow today, so we'll see how much I get through here. But if you have any questions on Laplace transform or comments, thoughts, just let me know. Okay, so what I'm going to do now, this isn't in the typed notes. What I want to do is, I promised you I would show you how you can get the impulse response of a dynamical system using the Laplace transform. I'm going to show you that. I'm also kind of just going to give you a conceptual overview of transfer functions and how to work with systems in the frequency domain. So I think this is going to be helpful. We're going to revisit a problem we looked at before. So we're going to be looking at the RC circuit or the power grid example. So as before, we have a RC circuit, some voltage source. Okay, we're treating the bulk resistance of the power grid as this resistor. We have a storage element corresponding to a capacitor. Okay, for this case, we're going to assume all initial conditions are 0, just for the sake of demonstration here. And we're going to call the voltage input from this voltage source, just for, bless you, we're going to call this UT. So the voltage source we're now going to call UT. The voltage across the capacitor we're going to call YT. And so putting it in terms of the standard names for our input and output, the resistance is R, capacitance is C. Okay, so we know the dynamical system for this RC circuit is given by dy by dt plus 1 over RC times y is equal to U. Okay, where in this case, I'm just using new variables here, but y is equal to our voltage across the capacitor, and the voltage input V is equal to U. Okay, so I'm just using these variables to put it in terms of the standard input and output notation. Okay, so let's see what happens when we go and apply the Laplace transform to this differential equation here. Okay, so let's go ahead and take Laplace of dy by dt plus 1 over RC y. Let me put the t's here. Yt is equal to ut. Welcome. Okay, so what do each of these terms become when we apply the Laplace transform? Let's use the properties that we discussed earlier. Okay, so what does this first term here become? Right, so it'll become sy of s minus what? Right, so the y of 0. Okay. Note that we said that all initial conditions are 0, so this becomes 0 for the purposes of this demonstration. Okay. Okay, what does this second term here become? In the frequency domain? What does yt become in the frequency domain? Yeah, just big Y of s. Okay, so we'll take this. So this will become 1 over RC big Y of s is equal to, and what does ut become? Big U of s. Very good. All right, so we can take this. Note here that ys, big Y of s, we can factor out. So I'm going to move to a new page real quich. How much time do I have? 15 minutes? Okay, All right, so let's factor out y of s. And we get the following equation, y of s times quantity s plus 1 over RC is equal to big U of s. All right, and now we can simply divide by s plus 1 over RC, and we end up with y of s is equal to 1 over s plus 1 over RC all times U of s. Okay, what does this equation remind you of? Does it remind you of anything we looked at before? Right, this is the same as the characteristic equation, except now this is actually multiplication. So now this is an actual multiplication problem where we are looking for the root of this characteristic equation, essentially. Okay, so just some terminology here. This function here is called the transfer function of the system, which we will denote by big H of s. So this is the transfer function. And this is equivalent to the impulse response in the frequency domain. Okay, so if you had the impulse response function and you took the Laplace transform of it, you would get this expression here. And vice versa. If you have the transfer function, you can take that and take the inverse Laplace transform and get the impulse response. Okay, so let's go ahead and do that. Let's say that we have an impulsive input. We have an impulse input to the system, and we're going to compute the response to that impulsive input, right? So ut is equal to delta t. What we're going to do is we're going to take the Laplace transform of that and see what we get. So in general, when we're solving these problems, we won't actually apply that integral. What we're going to do is we're going to go to our handy table of Laplace transforms, which will hopefully open for me right here. And there we go. And we go through this table, we find a function in the time domain and find its corresponding function in the frequency domain and vice versa. So what does a Dirac delta in the time domain correspond to in the frequency domain? 1. So we can go back here. U of s will be simply equal to 1. Okay, so we have from before, we have that y of s is equal to 1 over s plus 1 over RC times U of s. Our U of s now just becomes 1. And so we get that the response, y of s, in the frequency domain is equal to 1 over s plus 1 over RC. Because we've just multiplied by 1 here. That's our input. So let's go and see if we can take this response and convert it back to the time domain to see it in a more interpretable form. Does it look like any of our terms here in our Laplace transform table? Which one? This one, right? 5? Oh, sorry. Thought that was a 4. So a function of the form 1 over s plus a, where a is some constant, will correspond to a function of the form e to the negative at, right? So here we have 1 over s plus 1 over RC. So our a is 1 over RC. Therefore, if we take the inverse Laplace transform, what we get is yt is equal to e to the negative 1 over RC times t. All right. And this is equivalent to our impulse response. And you know what? I realized I did this wrong. There should be a 1 over RC here. there should be a 1 over RC in front of this U. So let me go ahead and redo that here. So this becomes 1 over RC U of S. So note that when I monetize this equation here, both the left and right side needed to be divided by RC. So let me just go back and rewrite that here. So this becomes 1 over RC U of S. On the numerator, you have 1 over RC. And this becomes 1 over RC. And here you get 1 over RC. And so everything was just multiplied by 1 over RC. And that is the same impulse response we found last time using the hand wave method. Okay. Great. Okay. So let's say we have an input to the system that isn't so simple. Okay, let's say we have a step input. Who knows what I mean by step input? You know what I mean by step input? Right. So it's going to be a function. I'll often write it as ut is equal to 1t for t greater than 0. And so what this corresponds to is if you have the number line here and you have ut, ut is 0 up until time equal to 0, and then it becomes 1, constant of 1. So for the RC circuit, this is equivalent to hooking it up to a battery with a constant voltage input of 1. Okay, so this is 1 here. Okay, so let's say we have a step input. We know that our system is of the form ys is equal to 1 over RC times s plus 1 over RC times u of s. What is our step input in the frequency domain? Let's take a look here. Note that they express it here as u of t. So this is the step input or Heaviside function. And it corresponds to 1 over s in the frequency domain. So let's go ahead and substitute that in. We have that y of s is equal to 1 over RC over s plus 1 over RC times 1 over s. And carrying out that multiplication, we get 1 over RC. On the denominator, we get s squared plus 1 over RC times s. Okay, so let's see, can we take this and go back to the time domain? Let's go back to our table of Laplace transforms. Remember, our function in the frequency domain is 1 over RC over s squared plus 1 over RCS. Is there anything here that corresponds to a function of that form? Well, it's not quite. It's close. No, it's not 8 because you need the s term on the denominator, right? S squared plus. Right. Okay, so Aditya knows the answer. Essentially, the way to solve systems of this form is to use a technique called partial fractional expansion. Okay. So I don't know if I'll have the full time to go through this. I've been going a bit slow this semester. But essentially, we can solve systems with an arbitrary form like this using a technique called partial fractional expansion. So it sounds like a few of you have encountered this before. Who's encountered this technique before? Okay, great. All right, so often it's easier to compute the inverse Laplace transform by using partial fraction expansion. So let's say we have a function in the frequency domain that is of the following rational form. Let's say we have something b1 s to the m, as in Mike, plus b2 s to the m minus 1, as in Mike, and so on, all the way to b m plus 1. So that corresponds to our input. And the denominator, we have s to the n is in November, plus a1, s to the n minus 1 is in November, and so on, all the way to an. If you have a function of this form, you can factor it. Okay, so this can be written as a product from I equals 1 to m as in Mike of s minus zi, where zi are the zeros of the numerator, or the roots of the numerator, over a product I equals 1 to n as in November of s minus pi, where pi are the roots of the denominator. So let me just write this out, because we'll be using this terminology later on. Zi are the zeros of the system. Okay, so these are the roots of the numerator. Pi are the poles of the system. And you'll see in subsequent lectures why they are called that. But essentially ZR are the roots of that numerator, Pi are the roots of the denominator. Okay. If you have roots that are distinct, we can take this rational function where the numerator is the product of s minus the roots, denominator is the product of s minus the roots. And you can write that in terms of its partial fractional expansion as C1 over s minus P1 plus C2 over s minus P2, and so on to Cn, the nth term, s minus Pn, the nth pole of the system, or the nth root of the characteristic equation. Okay, so this gives us a way of breaking up our rational function that we showed before. So remember that when we multiply the transfer function by the input, we get some rational polynomial generally that can be factored into its roots. What we can do is for each root, so let's just take the first root, we can multiply through by that root. Okay, so we'll get C1 plus C2 s minus P1 over s minus P2, and so on to Cn s minus P1 over s minus Pn. Then we can take this and we can evaluate it at s is equal to P1. Okay. And so what happens to this term here? If we evaluate s equal to P1, this becomes 0. This becomes 0. And what we end up with is this expression on the right, s minus P1 f of s evaluated at s equal to P1 is equal to C1. And you can go through and you can do this for each of the roots, P1 through Pn. And from that, you can determine those coefficients. What that'll give you is it'll allow you to put your system's response in the frequency domain into that nice set of individual terms, C1 over s minus P1 all the way through Cn over s minus Pn. You can take the inverse Laplace transform on each of those. And because the Laplace transform is linear, you can just add those together and get the response in the time domain. I don't think I have enough time for the example. We'll start with that as soon as we reconvene on Tuesday? Yeah, Tuesday. Today's Thursday. With that, go ahead and have a nice weekend. Take a look at your homework and come and see me if you have any questions. Right. Thank you.